We're about to find out that when you run current through a coil, that coil stores energy. So follow me along this argument. I want to start by making three conceptual points about energy transfer in a circuit. So the energy added to a system, and that system here will represent a circuit or a portion of a circuit. The energy added to a system is equal to the work done on the system by applied forces. And applied forces means these two things. Any external forces, so such as forces from a battery that's not being included in our system, or any internal forces that are non-conservative. Namely here, that would be the kind of drag forces that we encounter as our current moves through a resistor that converts our energy into heat. Those would be internal but non-conservative forces. So those would be considered applied forces, and they can potentially do work on the system that changes the energy of the system. We can kind of summarize that with this statement here, that the change in the energy of our system is equal to the work done by these applied forces, which includes the work done by the external forces and any non-conservative internal forces. This would normally be negative work here, removing energy from the system as our resistor converts it to heat, and this could be positive or negative here. Okay, point number two. When you turn your circuit on or off, the change in the kinetic energy of the system is really quite negligible. Recall that the drift velocity in our drift velocity model for current is much, much less than the speeds of the, as our drift speed here is much, much less than the speeds of the random motions of those electrons bouncing around like crazy inside your conductor. Our drift velocities, our drift speeds are something like 10 on the order of 10 to the minus fifth meters per second, as compared to the random motions, which are like 10 to the plus sixth meters per second. So turning your current on or off changes the average speed of your electrons by about this much compared to this much. Totally negligible. You're not changing the kinetic energy of those moving electrons in any measurable or noticeable way when you're making changes to your circuit. So as we're talking about energy transfers, any delta Ks we can ignore. Thirdly, now that we know that energy changes are due to work done by this category of applied forces, let's look at those more closely. The work done by these applied forces we can show is equal to the work done against the electric field. So starting with our work energy theorem here, representing the net work done in our system as the work done by the applied forces, plus work done by any conservative, C for conservative here, forces. So our work done by applied forces, that's work done by external forces plus non-conservative internal forces. Not included here would be work done by conservative forces. So the sum of these is delta K, which we've argued is negligible. So the work done by our applied forces is equal and opposite to any work done by any conservative forces on your system. So what might those conservative forces be? Well, we know the magnetic force is not going to be included here. Magnetic force never does work since the magnetic force is always perpendicular. The magnetic force on a particle is always perpendicular to the velocity of that particle. So magnetic forces do no work. Gravitational forces will be negligible compared to any electric forces in the system. Gravity is incredibly weak compared to our electric forces, so we can neglect any work done by gravity. Thus, the only conservative force that's going to be doing work is the electric force. So basically, all the energy transfers and changes in our circuits are due to work done by electric forces. Hence, we arrive here. Changes in energy of our system are going to be due to the work done by the applied forces against the electric field. So the work done by the applied forces will be equal and opposite to the work done by the fields in our system. This will be the basis of our calculation for showing that an inductor stores energy. So our conclusion there was that we can compute the energy stored in a system, let's call it energy U, the energy stored in a system, by summing all the work done against the electric field in the process of assembling the system. So as we build our system up, we've got to do work against the electric fields that are present, and that work that we're doing against the fields ends up as energy stored inside our system. Let's consider a small amount of work done by those applied forces, those external or non-conservative internal forces. An infinitesimal amount of work required, dWA, required to move a small amount of charge. So the work done by applied forces must be equal and opposite to the work done by the electric forces, by the electric field in our system. The work done by an electric field is defined here as the electric force on some small amount of charge. If the charge is infinitesimally small, then the electric force acting on it is also infinitesimally small, because our electric force equals Q times the electric field. And if that electric force is doing work along a path, this is our path integral here with a little displacement increment ds, then the small amount of work required to move a small amount of charge dq along some path against the electric field, that minus sign there is is sort of the mathematical indication of this concept of against. We're pushing against the electric force along a path against the electric field is equal to this. This is what we wanted to show. So we're going to be able to find the work that's required to set up our system from this integral over here. So we're going to be imagining taking some little bit of charge dq and moving it along some path and comparing it to the electric fields that are present that we have to push that charge against, sort of lift that charge against the fields, or push that charge through a region of field to add energy to our system. Okay, I would like to do side by side this calculation for a capacitor and for an inductor, because I think it's illustrative to compare the two cases. This capacitor argument we've done before, but we're revisiting it now, and we'll sort of walk through it again in light of how it's similar to and different from our argument for the inductors. And so we'll see how both systems end up as energy storage systems. Speaking of system, I've got a simple circuit here with a capacitor, a resistor, and a battery. Here we have an inductor, a resistor, and a battery. The system will include just our capacitor here. So we're looking at the energy added to our system. That's just the capacitor. So we're going to consider our battery and resistor to be external to our system. Likewise, over here, our inductor will be our system, our coil, and this battery and resistor will be external to our system here. So as we're talking about the work done on our system, that applied work here, this will be the thing doing this applied work is going to be the battery and this battery. The battery is external to our system here, and work done by the battery is going to be adding energy to our system. And work done by this battery is going to be adding energy to our system. So we're basically going to be transferring energy from the battery into the capacitor, and here from the battery into the inductor. So as I say, the work we do, what I'm going to mean is the work done by the battery, meaning the work done by the chemical reaction occurring inside the battery. That is the external agent doing this applied work right here. Okay, we need a path for this equation to make sense. So what is the path that we're moving some charge through? In our capacitor, let's say this top plate here will have a charge on it that'll be a function of time that I'll call Q of t. So let's say we're going through the process of charging this capacitor up from initially storing 0 excess charge on this top plate. So Q of t will be start at 0 and will increase over time. It'll be positive. And we charge it up by taking some positive charge, dq, some small amount of positive charge represented by this little pink dot, and we're going to do work to lift this positive charge against the electric field to bring it up to the top plate. We're going to carry it from here to here. Although not directly across the gap in our capacitor, we're going to push it all the way through this circuit to get to there. So it's the battery doing work to sort of lift this charge up to add it to our top plate. And as our top plate gets more and more positively charged, it'll become more and more difficult to add additional positive charge to it because it's going to repel additional positive charge. So we have to do work to lift this charge up. So here's our path. We're taking this positive charge dq. Okay, and yes, we all know that it's actually the negative charges that move through the circuit, but we also know that mathematically, imagining positive charges moving is equivalent, so it's not a problem. Take this imaginary positive charge dq, starting here on this plate, and take it along a path, moving in this direction, through our battery, through here, up to our top plate, and end there. So this is our open path. We don't end back where we started, we end somewhere else. We start at the bottom plate and end at the top plate. So there is our path that we're moving along. Okay, for the inductor over here, let's start with some positive charge dq located up here, and we're going to imagine pushing it through the coil, through the battery, all the way back to where it started. So this path is going to be a closed path. Our goal here is not to pile up charge somewhere, like in the capacitor where we're piling up positive charge on the top plate. Here, we're not trying to pile up positive charge. We're not storing energy by separating charge. We're going to be storing energy by increasing the current. By adding current, it's going to turn out that it requires energy to do that. So our goal here is to make sure that this charge is continuously moving through the circuit. Not just added to one place where it will stay, but continuously cycling through. So we're going to take it on a path that starts here and then spins all the way through all the turns of our inductor, through the battery, and back to where it started. So we've got a closed path here for this bit of charge. So the goal is to keep that charge continuously circulating, hence the closed path, as opposed to this charge pile-up, charge build-up based open path. All right. So let's go to our Kirchhoff and Faraday's laws. To motivate the idea here, let's think conceptually about why it's going to take energy to do what we're trying to do. Once again, here our battery is going to have to lift this charge up to get it up here to a higher potential. This plate's at high potential, this plate's at low potential once we start getting positive charge up here. So it takes energy to lift this charge up, put it up there. That's what the battery is doing. We have to go against the electric field inside our battery here. Essentially, the chemical reaction in the battery is doing the work to lift this charge up from low potential here to high potential here. This is our battery acting as that sort of escalator to raise charge up to higher potential, moving against the electric field inside the battery itself. That's what these green lines represent, the electric field inside the battery itself. So along this path, we do have to move against the electric field to get up here. So this is us doing work against the electric field to raise the energy. Over here, moving our charge through the coil, we're actually moving with the electric field everywhere we're moving through the wires. If the wires obey Ohm's law here, then our electric field always points in the direction of the current. So we are going with the electric field here. The electric field will only be as big as it needs to be based on the resistance of the wires. So if these are low resistance wires, if our resistivity here is small, then this field will be small. So we're sort of moving with the field here, which shouldn't require any energy at all. Just like over here, there will be a small electric field pushing us through that resistor. Small electric field based on a small resistivity here. So that's moving us with the field. So that shouldn't require energy. It's the moving up through the battery that requires the energy. Here's where the chemical reaction lifts our electrons, does the work to move them against the electric field here. Likewise, over here in this case, it's our battery, the chemical reaction in the battery doing the work to lift our electrons up from this low potential to this high potential. That's where the work is happening in this path. So yeah, we move with the electric field as long as we're in the wires, but the big work, the big work that will result in our network is here, lifting us through the battery. Okay, so let's go to our Kirchhoff and Faraday law here. I guess one more thing. Lastly, I want to point out that just as this plate is at high potential and low potential, the top of our coil will be at a higher potential than the bottom of the coil. This delta V is not due to an electric field like between the plates here. This delta V, this EMF across our inductor, is due to this little term right over here. That's due to the changing magnetic flux due to the changing current in our coil. This is your Faraday term right here. It's this Faraday term due to the changing magnetic flux, the electromagnetic inertia of the system, that's causing an induced EMF, a self-induced EMF, a back EMF across your coil. So in this case, the top of the coil is at a higher potential than the bottom of the coil. So moving our charge through that coil is similar in some regards to moving our charge across this potential difference, starting at low potential and ending up at high potential, starting at low, ending up at high, except we go all the way through the coil, all the way through the loop in this case. All right, anyway, that'll make more sense as we look at the equations. All right, so stating our Kirchhoff law for this capacitor path, delta V equals minus EDS along that path. There's no Faraday term here because no changing current, no magnetic stuff going on. For this path here, for this closed path, we end up, if we start here at this V and end at that V, then the delta V is 0 for this closed path, but we have this magnetic term due to the changing flux to compensate. So, okay, next line. The small amount of work it's going to take to move that dq from here to here along that path equals minus dq times this integral. We derived that up here, so I'm saying this small amount of work is equal to this expression here. And our Kirchhoff law says this integral of E dot ds along our path is equal to minus delta V. So that minus and that minus cancel out. We have dq times delta V here. So the work it requires to lift dq from here to there is just dq times the potential difference from here to there. The net delta V we know is equal to the charge on that top plate of our capacitor divided by C, the capacitance of our capacitor. Okay, over here, the small amount of work it takes to push that charge all the way through our closed loop, minus dq times, this is our closed path integral, E dot ds, and we show here that minus E dot ds is equal to L di dt. So minus signs will cancel out, and we get plus dq and replace this with L di dt. So in comparing these two, we've got this delta V here across our capacitor, and this term, which is acting like a delta V across our inductor here. It is indeed a delta V. It is a potential difference. This is our EMF across our inductor, our self-induced EMF, our back EMF. That's our L di dt, in magnitude anyway, right there. So both these are our delta V's. All right, we're just about done. What we need to do is add up all the work it takes to move all the charge we want to move up there, and then add up all the work it takes to move all the charge we want to move at the rate we want to move it through this coil. So we're going to add up all the dWs, so we're adding up the dq times q over c, as q goes from some initial charge 0 to some final charge, positive q, big Q. That integral gives us 1/2 times 1 over c q squared, an expression we've derived before, but here once again we've rediscovered the energy stored in our capacitor, U in our capacitor. That's what our capacitor is storing. It's based on the charge in it. Now, over here, we're going to add up all the work it requires to push charge through this coil. So adding up all those dWs, I'm going to take this dq, and since our current is dq dt, then dq equals I dt, a small amount of charge passing by a point equals the current passing by that point times the small amount of time that elapses. So this dq is I dt, and here I can say our dt and dt cancel, so we're left with L I di. What we want to do is integrate as we start from 0 current At the beginning, once we close the switch to start this, there's no current flowing initially. Recall that with an inductor present, it takes time to build up a current in a circuit. So we start with 0 initial current, and we're going to build up to some final current, capital I. Big L, our inductance, is a constant, so the integral of I dI gives us a 1/2 I squared, leading us here. We've discovered that there is energy stored in an inductor. The expression is given by 1/2 the inductance times the current running through that inductor squared. Compare the two. A capacitor stores energy by having some amount of charge on it. An inductor stores energy by carrying an amount of current through it. And note here that this doesn't depend on the rate of change of current. Here, the inductor is storing energy as long as there is current flowing. And the more current there is flowing, the more energy is being stored. So note the similar construction of these two. 1/2 times a factor that characterizes the device, the capacitance here, or actually the reciprocal of the capacitance, and L, and then something squared. Q squared in the capacitance case, that's how we store energy, by storing charge, and then I squared in the inductor case. We store energy by running current. So apparently it takes energy to build up a current through an inductor, and that energy is somehow stored in this system.